So let's get started. Oh, this doesn't work. Yeah, so what is this course all going to be about? So the challenge oftentimes in machine learning is to actually understand complex and highly structured data or unstructured data. So you could think about large collections of images, as you see here, as oftentimes encountered in the field of computer vision. You could also think of speech as unstructured data, right? It's basically an audio signal, which looks very complicated. You can think of natural language processing. So you have a lot of unstructured text that you would like to understand. Or generally also robotics is an example where you don't really have a lot of structure in your data and you still want to learn from it. So this course tries to deal with finding hidden structure and making sense of these unstructured data, in particular if you have a lot of data available. And in particular, it attempts to generate these kind of data, such that the generated data almost looks undistinguishable from real-world data that you used in order to train your machine learning model. And this might actually remind you a little bit of the analogy between computer graphics and computer vision, right? Because computer graphics also deals with, the problem of generating data, right? Think of a computer game engine. You have to kind of generate scenes, but it's very different in certain regards, right? So computer graphic typically deals with a high-level description of the things that you want to display. So for example, you might say, I want to draw a cube, which has a blue color, should have a certain position and a certain size. Maybe I also want to draw a cylinder, which should be red and which should also be located at a certain position. And then the computer graphic engine would typically render this and would display it on your computer. So you can think of that also as a generative model, right? So kind of it generates images based on a certain high-level description. But this is not really what we mean when we talk about generative models, right? So in some sense, you can think of computer graphics as one end of a very extreme case in which you have a lot of prior knowledge about your world. You know all about its geometry, kind of how certain sizes and lighting conditions affect the appearance of an image. So you need a lot of prior knowledge about geometry and physics in order to generate images using computer graphics. And then typically there's also the opposite process where instead of starting with a high-level description, you go down to kind of the pixel level output. You can also start with the raw camera images or the raw pixel level information and then try to extract the higher level information, right? And this is oftentimes called inference in vision. For example, you might want to think about a detector that detects edges such that you then can reconstruct the three-dimensional geometry of certain things that you see in a video, for example. But as I said already, this is very different from what we're trying to attempt here. We want to attempt to generate natural data or realistically looking data, for example, natural images, without any such prior knowledge or with very limited prior knowledge. Right? Can we sort of generally generate realistically looking images in a fully data-driven approach? So this actually leads to the concept of statistical generative models, which are, if you will, statistical models that are learned on a lot of data. So basically, we have data on the left-hand side. So think about a large data sets of, for example, bedroom images that we'll encounter many times in today's lecture. And also a little bit of prior knowledge about the world, for example, knowledge about physics and materials and so on. And it turns out that this prior knowledge is always necessary if we want to generate something. Right? Sometimes it can become more important, and in other cases less important, but generally you need some sort of prior knowledge. But if you want to again distinguish this course from a computer graphics course, you can think of different generative models being sort of on an axis that require different amounts of prior knowledge. So for example, computer graphics would need a lot of prior knowledge about physics and geometry and light conditions and so on. So it's very far on the right-hand side, whereas in this course, we are very much on the data side. So we assume very little knowledge, and most of what we learn is going to be fully data-driven. I think there was a question somewhere here.
Oh yeah, can you turn down the light?
Sure. Let's see. Screen. Oh, okay. Yeah. thing is, I don't want to sort of mess things up too much here. Let's see if I can dim the light here. No. Is it really bad, or is it okay for today? Maybe next time I can try it out. Can you still see something? Yeah, next time I'll learn how this works. All right. Okay. Right. So we're pretty much on the data-driven side here. We assume very little prior knowledge, and we let the data speak as much as possible. All right. So let's talk a little bit more then about statistical generative models. So statistical generative models can be thought of essentially or a generative model can be understood as a probability distribution ultimately, right? So you want to learn some distribution, some model of your data X. And so let's call that model P of X. So that model clearly requires data, such as typically in the form of samples. So think of data sets, for example, images of bedrooms. And as we already discussed, we also need some prior knowledge that we want to exploit. And that can be either assuming a certain parametric form for our distribution. For example, we could say we work with Gaussian distributions, which is fairly limited, but later on you will learn much more powerful ways of parameterizing distributions, but that would be a choice, prior knowledge. Another one would be the loss function that you use. For example, do you want to use maximum likelihood training, or do you want to use adversarial training, for example, as used in GANs? And that's something, again, we learn about later. You can also choose on an optimization algorithm, which might affect the result. And that's like another example of prior knowledge. Then, as I said, so the generative model is that probability distribution P of X in the middle that assumes images or other forms of data as inputs and assigns probability to every possible image. Right? So why is it called a generative model? It's called a generative model because you can actually also sample from probability distributions, right? In other words, you can generate data from it. And in the context of generative models, or deep generative models, we often think in terms of very high dimensional data. So in this example, it really means that we can generate images if we sample from our trained model. So for example, if you trained it on bedroom images, then sampling from the model will also generate bedroom images like the ones that you see here. So how is that actually different from what you've probably mostly learned about, maybe in introduction machine learning courses, namely discriminative models, right? So if you attended like an introductory machine learning course, then discriminative models is pretty much everything that or most of what you learned about so far. So just as a reminder, in discriminative modeling, you're typically interested in either regression or, for example, classification. So here, as an example for a classifier, you might have images of bedrooms on the right-hand side, lower right, and you might have images of living rooms on the upper left-hand side. And then the goal is that you will actually learn to discriminate them. So the input of the model would be always your images, X, and the goal is to learn a good decision boundary that allows you to separate one class from another class. So typically, for example, using a conditional distribution used in, think about logistic regression, convolutional neural networks, or anything like that. Right? So then you would learn that decision boundary in that high dimensional space. And that's different from, And one way to think about it is that this actually also sometimes involves probability distributions, namely a probability over possible labels, bedroom or living room, right? Given that input image, which is, for example, the raw pixel information, as this notation here should allow you. And then, for example, for that particular image, which actually shows a living room, the probability that this is actually a bedroom would be very low, right? So for example, 0.01. Can you see that roughly? Or, all right. Okay. So what is then the difference to generative models? And okay, maybe I'll have to quickly Let me just leave it like that. No. Okay. All right. So what's then the difference in a generative model? Typically, you would jointly model the data X and also the corresponding labels Y. And that generative model would then output an array of all possible options that could be true, right? So for example, you could have that, the probability, you would assign a probability that the image actually shows a bedroom, so Y equals B, whereas the pixel level input X here would be this particular image of a living room. You would also assign a probability for the other case where the label is dining room and you actually show an image of a dining room. You would also learn probabilities over, the image showing something completely different, unrelated to either living room or dining room, and both probabilities that are associated with that, or the probabilities that an image actually shows a bedroom and the label is either bedroom or dining room. Right, and all of these combinations have non-zero probabilities under that generative model. So that's very important. So you actually really model the combinations of probabilities for X and Y together, right? So every combination has a certain probability under that model. That could be either large or that could be small. So for example, here, the joint probability that the image shows actually a dining room and the label is bedroom would be a very small value, 0.0001 or 2. Okay. All right. Okay. So it turns out that generative modeling is oftentimes more powerful and more expressive than discriminative modeling alone. And the reason is that you get these conditional probabilities that you start with in discriminative modeling. You can actually also get them when you do generative modeling. And the way you get these conditional probabilities is using Bayes' rule, right? So this is just like a reminder that the conditional probability of Y given X is given by the joint probability of P of Y comma X divided by the so-called marginal probability P of X, right? So in other words, the probability of that given image irrespective of its label. And that's very different from discriminative modeling. Here, in discriminative modeling, X is actually always provided. It does not explicitly have to be modeled. So that's actually the difference, right? So you never need to know that posterior normalization constant. And that oftentimes is actually kind of difficult to obtain. So one of the advantages of generative modeling is that it can actually handle missing data. So for example, you could partially obscure an image and still be able to know whether the label is bedroom or not. Whereas in purely discriminatively trained models, you always need the full image input in order to make that decision. Okay. So it turns out there's also something called conditional generative models or class conditional generative models. So far we only talked about models that generate data and you have no control about what these data points look like that you generated from the model. But you could also specify a certain site information and then conditionally generate something. Right? So for example, if you wanted to only generate dining room images, you can train a model that exactly achieves that. Right? So this would be then a conditional distribution P over these pixels, given that the label is either dining room or living room. And so that actually oftentimes is very useful in applications. So for example, there are papers that allow you or that show that you can actually conditionally generate images by specifying a textual description of the image. Right? So for example, you could say generate or like a black table with 6 chairs, and then hopefully that model would exactly generate an image that would depict that. Right? So that would correspond to modeling the conditional probability of the image given a textual description from it. And in a way, this is actually then, again, very similar to discriminative models. right? Because there, it's just the other way around, right? The input is the image, and then the output would be a label or a description of the image. But typically, we like to think about generative models as going from low dimensions to high dimensions, right? Whereas typically in machine learning and discriminative modeling, you have a high dimensional input and your output is low dimensional. For example, a binary decision. Okay. All right. Any questions yet? All right. Okay. So it turns out that there is kind of a typical class of deep generative models that one usually thinks about when somebody mentions the word deep generative model. And I guess a lot of you who have already heard about the term before think about deep generative models as variational autoencoders or GANs, generative adversarial networks, right? So those are typically important classes of models. And here, I just want to give a high-level description of what these actually do. So think about like the space of all naturally looking images as a sort of complicated submanifold of a higher dimensional space. So certainly the space of all possible images is huge because every pixel can have its own color value out of 3 color channels and then 255 color intensities, right? And typically you have 1000 by 1000 different pixels. So it's like a huge combination of possible images, but all the subspace of images that actually look natural, that has a certain structure, is typically much smaller. And we like to think about it as lying on a sort of a curved subspace, like in other words, a submanifold of the very high dimensional space. So you can think of that as that blue object that I drew here. And then on that manifold, there are certain points highlighted here showing very different things. So for example, there could be a car image sitting here, a horse image sitting here, and a tree image sitting somewhere here. And now the goal of these generative adversarial networks and variational autoencoders is to actually trace out or map this entire space of naturally looking images. And the trick is to start in a typically lower dimensional space, which has an easier structure. For example, it might be spherical and lower dimensional. And then to learn this mapping, this nonlinear mapping from the lower dimensional space, which we also sometimes like to think of or call the latent space, onto that high dimensional space of naturally looking images. And unsurprisingly, this is done with neural networks, right? Neural networks are universal function approximators, so they can be used in order to learn or morph that low dimensional space to the high dimensional one or the curved space. But it's not immediately obvious how to train these models, right? And this is essentially what all this course is going to be about, right? I mean, what are the training paradigms that allow you to do that unsupervised learning of these high dimensional image spaces, right? Or this is at least parts of what this course is going to be about. Yeah. So you see now that every point here gets mapped to a point here. So that can be then used to, in other words, there's sort of an origin of every image in this high dimensional space, which is sitting in the low dimensional space. But you can also think of the other way around. Imagine that you have actually a natural image sitting somewhere here. You could theoretically look up its position in this original source space, this latent space. And that can be thought of as a way of compressing these images, right? Because you started in the low dimensional space. You know, when you're here, then you can just apply that neural network transformation and it generates the original image back. So you can use that lower dimensional vector here as a compressed version of your image, right? And this is actually one of the most interesting current applications of deep generative modeling in the image and video space, is to actually try to revolutionize the way we do compression. And we'll learn about that later in this course. Yeah.
Is there anything inherent about some of these architectures like VAE that is Gaussian, or in theory you can use any distribution Gaussian?
Yeah. So the question was is there anything inherent about these VAEs that is Gaussian, or can we kind of use any other distribution? So the only reason why we use Gaussian distributions so much is that they're easily to work with, right? I mean, you can easily sample from a Gaussian and evaluate probabilities, but there are also examples of VAEs that are using non-Gaussian distributions. They're just a little bit more difficult to handle. Yeah. All right. Okay. Yeah, so here I wanted to play a video. I think this is probably not going to work the way I wanted to. So if you want, you can just click that link at home. So this is just like even not the most recent results. So this is even like 3 years old, but you can see how amazingly these models already work. So basically there's no way anymore to decide between generative models and real world images nowadays, right? If in particular, when it comes to face images, let me actually still do that. It's so much fun. Probably we might have to wait some, hopefully there's no advertising. No, of course there is. Yeah. I mean, this is just kind of giving you some idea. Like each and every, you could stop the video at any point and it would kind of generate a realistically looking face. And moreover, these models also allow you to morph one face into another one. So you can actually watch this for as long as you want. And it's pretty impressive, right? And this was 3 years ago. I mean, by now things are even totally undistinguishable. So anyways. All right, stop that and go back to the lecture. Okay. So for the next few minutes, I want to give you a couple of examples. So far we only spoke about variational autoencoders and GANs, but there is an entire zoo of generative models that you're going to be learning about in this course. And one of them is called autoregressive models, one class of models. And autoregressive models are typically conditioned on what's been already generated and take all of that into account to generate the new thing. So oftentimes this is used for sequential data, for example, for voice audio or any other forms of audio. And so what then happens is that all of this audio signal is going to be fed into the network, and then a new sample is being generated as visualized here. So we'll learn all about these models in a bit, but here I just want to highlight how impressive they are. And here probably have to apologize to the folks who are on Zoom because the audio typically doesn't work there. So let's see if it actually works here. You can always watch the lecture later. See if I can play that. I'll probably have to just use my computer audio. Oh. Why is it turned off? That's so much fun. It's really a shame when I get it to work. For some reason, it's forbidding me to play audio now. I don't know why. See if I play it again. Nope. Maybe disconnect. Turn that off. Yeah, nope. Never mind. Yeah, it's a shame. Those are kind of really cool audio clips, so I highly recommend that you watch them at home. So basically, they can be used to generate voice. Think of Siri and other voice assistants. They can also be used to generate music and piano songs. So it's really nice to hear. And yeah, it's kind of pretty surprising that they're barely indistinguishable from any natural sounds. Okay. So another application of generative modeling is image super resolution. So what is super resolution? It's actually a technique that allows you to take like a poor resolution image and enhance its quality. It sounds like a little magical. It's technically impossible to generate more information out of nowhere, of course, right? If you have kind of coarse-grained the image to a lower resolution, information is lost, which can never again be restored. But if you know a lot about images and their structure in general, you can maybe transfer some knowledge that you had about other images to enhance the visual quality on a local patch level of an image whose resolution you want to increase. Right? So what you see here is like an image of a cat, and there is some kind of zoomed in region of a cat's ear. And basically, this might be a little bit hard to see here, but the original quality is pretty bad. And then if you do upsampling using a conditional generative model, you can actually restore in a pretty plausible way all the fine granular hair structures of that cat's ear, right? And you can do that also for the fur region. So that's kind of very popular for enhancing the quality of videos. For example, older movies whose quality you want to enhance again and make it kind of compatible with modern televisions. Yeah, here's another acoustic example, which I cannot really play. But the idea here is that there's also super resolution in the audio way for audio. So you can think of as an audio signal as pretty much as an image in the sense that there is time, in other words, audio frames. And then for every moment in time, you have a spectrogram, right? And that's kind of the vertical direction. Now, what oftentimes happens is that for different reasons, the high frequency information might be gotten lost, or maybe it's because you're wearing a mask or something, so the voice sounds unnatural. And maybe you want to kind of restore the voice using all the high frequency information as well. So what you can then do is you train a conditional generative model that takes the lower part of that acoustic signal and then generates everything that's missing, right? And if I could play the audio, which you can do at home, then you will actually see that this kind of sounds pretty good. Yeah. Another example of a generative model are machine translation models. I mean, those are kind of pretty specialized architectures that we will not probably talk about here in this lecture. They're also pretty specific to natural language processing, and we have dedicated courses on natural language processing already. But you can think of as a machine translation model also as a conditional generative model that takes a lot of high-dimensional text as input in one language and generates the text in another language, right? And as you all very well know, in the last couple of years, there were amazing progresses now, and basically, there's very little errors that tools like Google Translate nowadays do, right? So anyways. Yeah, and finally, there's also style transfer, neural style transfer. So that's kind of also a pretty fascinating field where you have different pairs of video or images even, right? For example, a lot of videos from horses and a lot of videos from zebras. And now you're trying to in-paint like the zebra pattern on the horse, right? And you can do that if you have a lot of data, and we'll learn more about these models in a bit. Yeah, finally, there are also conditional generative models that allow you to generate videos, right? So this is kind of, again, slightly older work from my group, but I mean, essentially you can train the model on a lot of little video clips of these walking cartoon characters and then generate from the model. And you can then do that unconditionally. This kind of gives you these little clips that you see here. But you can also specify, for example, the appearance and generate different motion types for that same looking character. Or you can actually condition it on the motion and then generate all sorts of different appearances. So this has something to do with so-called disentangled representation learning, and we might be able to talk about it also at some point. Yeah, as I also said earlier, compression is kind of one of the nice application areas also in generative modeling. So it turns out that with these variational autoencoder type models, and if you tune their architectures, and if you pay attention to the right kinds of metrics, you can actually achieve the world record in image compression performance, and replacing traditional codecs like JPEG and other established codecs in image compression. Okay. All right. Yeah, so what is then the roadmap and the key challenges in deep generative modeling? So there are many questions that we would like to address in this lecture. So one is, how do we actually model the joint distribution of many random variables, such as individual pixels in an image? Right? So as you can imagine, this is not a typical probability distribution. This is a probability over an extremely high dimensional space, right? Millions of pixels or potentially even more. So we need a very compact description of that model already, right? Because we cannot just write down a model that has millions of parameters. So we need to think about how can we compactly even represent a model that could achieve a goal like that. And then what we'll talk about a lot in this lecture is that topic of learning these generative models. So what is actually the right way to even compare probability distributions? How do we make sure that our model that sort of approximates the data distribution is actually close to the data distribution? How do we measure distance between our models distribution and the real data distribution, right? So here you see sort of the real world distribution over all possible images of dogs, and here you see maybe the distribution that our model outputs, and how do we actually minimize that distance such that we really capture the distribution over all dogs, right? And then we'll also talk about inference, which is the opposite of generation, right? So how do we actually invert the generative process? Right, so for example, given an image of a dog, how do we look up its compressed lower dimensional representation under a variational autoencoder? Right? Yeah, so we'll talk a lot about unsupervised learning because surprisingly, it turns out that usually supervised learning is more basic, and then unsupervised learning in an introductory machine learning course is a little bit more complicated. Here it's the other way around. In some sense, unsupervised is easier, and then supervised will be a little harder. Right? So we'll mostly talk about unsupervised learning and how we recover high-level descriptions of our data. Yeah. So this is sort of roughly what we want to talk about in this course. There's quite a lot. So we'll first start with fully observed likelihood-based models. So those are models that that have no latent variables that I talked about before. So there's no Z. So we only directly model the probability distribution in image space. And some of them are called autoregressive models, but we also talk about so-called flow-based models, so normalizing flows. We'll then talk about latent variable models, which is this idea that you have an underlying lower dimensional representation of your data points that you want to infer and use that for generation. And here we'll talk about variational inference, in particular also faster versions of variational inference called amortized variational inference, and this connects also to variational autoencoders. We'll then talk about so-called implicit generative models, which is yet another class of models where you you have a model that allows you to generate data, but you cannot really evaluate the probability of the underlying data points. And this oftentimes relates to these generative adversarial networks, in other words, GANs that you've heard about. So we'll learn about the training paradigms, and this makes it necessary for us to dive into two sample tests, embeddings and F-divergences, and ultimately we'll understand GANs. Then, and so basically everything else is kind of advanced. So we'll probably talk about deep latent variable models and structure. In other words, on the one hand side, we have deep learning, which gives you very flexible distribution approximators, and that allows you to do a lot of things in a supervised fashion, or maybe models for unsupervised learning as well. But then we also have latent variable models, which are interpretable and which kind of allow you to put a lot of prior knowledge into your generation process. And so we'll learn about how to combine latent variable models and deep learning in some sense. In other words, deep probabilistic modeling. And this relates to structured variational autoencoders, deep time series models, models over discrete data, and learning disentangled representations. And then finally, not necessarily last, but maybe infused over the duration of the course, there are applications and theory. So we'll learn about improving variational inference for achieving better results. We'll also learn about information theory a bit, because variational autoencoders have a tight connection with information theory, and that also draws the links over to neural data compression. So we'll also talk about compression. All right. Yeah, just a couple of prerequisites and warnings. I'm sure most of you are pretty strong in statistics and math and programming. So this is, like, as you all know, a fairly advanced course. In fact, it's the last one in this kind of whole sequence of advanced topics, starting with probabilistic modeling, and then Porrick-Smith's course, and so on. Not all of them are required, but they're recommended. So there's quite a bit of math, as you'll see, that is necessary to actually understand these concepts. Okay? But what's actually required? So you have to know about machine learning, of course. You should have either taken CS 178 or the corresponding graduate course, CS 273A. Right? As I said, recommended courses are other advanced courses in graphical models or maybe neural networks. And yeah, so just kind of get a feeling of what kind of maths you might need. So we'll certainly talk about stochastic gradient descent, well, neural networks, backpropagation, latent variable models, expectations, conditional independence, Bayes rule, and the expectation maximization algorithm. So hopefully all of this is fairly familiar to you. At least you have heard about them and roughly have an idea what these topics are about. And then also you need to know Python, and in particular PyTorch. So we'll not be able to offer any tutorials. And as you know, this is a graduate course, so there's no, so there's only the lecture. There are no additional sessions that teach you these things. So you're kind of expected to learn these things on the fly, essentially. All right. Any questions? Okay. Yeah, a couple of logistics. So hopefully you've all seen that there's a Canvas course page. So this is the link. So this will always be updated, hopefully, right? And you find the assignments, you'll find the uploaded links to the video recordings and also the lecture slides themselves. There's also like a page that has useful resources when you think about projects that might kind of get you started and where to look for and what the, what conference proceedings are kind of a good source for modern papers that kind of give you some inspiration for the course project. All communication should be done via Piazza, so please don't write emails, use Piazza. So that's going to be the quickest way, and there we have it all in one place. So here's a Piazza link. And then for homeworks, you'll use Gradescope. So there you kind of submit your homeworks, and they're going to be graded online. And also any regrade requests should go through Gradescope directly. So there's a possibility to ask for regrade requests there. Yeah, Aodong Lee is our TA. And for all office hours, they're going to be by Zoom, and you can actually conveniently schedule them using Calendly. So there are some reserved time slots there, and you can just kind of pick one, and then it's automatically appearing in my calendar or also in the TA's calendar. And it also has a Zoom link, so it's all super convenient to schedule. About other logistics and grading policies, so there won't be any exams, luckily. And there's going to be instead basically the project, the homeworks, and some participation credits. So for the homeworks, they're 45% of your grade. And this is going to be a mix of mathematical homeworks and also statistical and programming-based questions, right? Using PyTorch. So typically you have like some things to complement or some easy model to implement there. The other important thing is that there's no late homeworks, right? However, to compensate that, the lowest scoring homework will be dropped, right? So it's just not going to be taken into account. So this kind of compensates for any late homework policy, and typically students prefer that option. There's also going to be 10% participation credit. So importantly, the course evaluations are going to be part of that, right? So don't forget to do these evaluations, but there might be also other things like, which are not completely figured out yet, but potential quizzes, other forms of participation, how active you are on Canvas, things like that. And then finally, the course project itself, which is going to be another 45% of your credit. And for that, we'll have a separate discussion how that works. Any questions? There's no textbook. It's just like a new field for that. But I mean, there are certain review articles, and you'll find them also listed on the Canvas page. If you go to Canvas, there's like a resources link. The only real textbook that exists is actually the Benjo deep learning book. That might be useful, but it's not really covering generative models. How about the projects then? So they will be by default groups of 3 students, and they can fall into different types of categories. So you can do different kinds of projects. You can either suggest an interesting new application of generative models to a new data set, for example, right? So maybe you have a biology background, you have an interesting data set, and you just want to use existing models and test them on that data. That would be a perfect group project. Another one could be making actually algorithmic improvements on the evaluation, learning, or inference of deep generative models. So this is typically the most difficult one, and I only recommend that if you already have, if you're, for example, a PhD student, or you're at least pretty experienced and you really know, you really want to kind of change the training schemes, right? And hopefully get better results. But that's perfectly doable as well. And then finally, there's also the option of taking an existing paper and trying to re-implement it and getting the same results that were found in that research paper. And that can be actually also very rewarding, and it's not going to be easy. So if you don't know a lot, you don't have a lot of ideas about the first two options, I highly recommend the third one, and you're going to be learning a lot. And I should also say that your grade does not depend on any of those choices, right? You can do a bad or good job with any of these three options. And so our course website provides also a list of possible papers and further references, and we'll constantly update and add more papers to that list. Okay. So some more information about the details of the project. So made some good experiences with not having the whole credit be the final projects, but rather sort of distributing the credit along the way there. So typically, there are two intermediate milestones, which are actually pretty easy. So the first milestone is very simple. After a couple of weeks, the only thing that we'll ask you for is to specify your team, right? So maybe you can already start looking for team members. And just by specifying that team, and we'll tell you exactly how, you'll already get 10% of that course project credit. Pretty easy, just kind of giving you some incentives to do it early. If you don't do it, then you don't get that early team formation credit. Similarly, a few weeks later, there's going to be another intermediate milestone, and that's your abstract submissions. As you all know, abstracts are very short descriptions of a research paper, typically only 6 sentences or so. And I want you to kind of write a very concise, short description. Actually, I kind of give you an outline of what every sentence could be about. And that just kind of forces you to meet with your project teammates and think about what you actually want to do and make that decision, right? And then you submit that abstract. That's another 10% of your course project. And of course, you can still change your minds, right? But at least you should kind of present your first idea. And then finally, there's going to be some meetings with me, probably someone at some point in November, so to figure out where we have probably Zoom meetings and talk more about the details of your ideas. And this should be 4. There's going to be finally a report, and that's going to be the bulk part of your credit. And the outcome would be a workshop style paper that resembles, for example, ICML, International Conference of Machine Learning workshops, which is typically like 4 pages, 2 column, and we'll also provide links to that format. Okay. Any questions about the course project? All right, so then some things that are hopefully clear to everyone. Well, first of all, I decided that I'm not going to ask for live attendance. So made some good experience with that. You're very welcome to join if you feel more comfortable and safer at home. That's also fine. It might also depend on any kind of COVID waves that we might still experience or not. Yeah, so you're welcome to join. We'll upload the sessions on the same day, typically in the evening. And I will also try to stream the videos live. So we'll see if it worked well or not. It might be a little harder, though, to ask questions. So I'm not sure if I'll be able to multitask and answer questions on both sides, but I'll try to. Yeah, and of course, then this thing about being required to wear a mask at all times. And if you feel sick, then please stay at home. Okay. Some other logistics. Homework 1 will be released today. So that's pretty much ready. And then the first deadline for the homework is a little bit shorter than usual. It's already going to be due on Thursday, October 7th. And the reason I'm doing that is that the course drop deadline is the next day. So I want to give you some early feedback if you're kind of comfortable with the level of mathematics that's going to be involved in this course. So I highly kind of recommend to take that into account. I want everyone to succeed, but unfortunately, there's always some people who are, have bad surprises with the level of math. So I want you kind of, this gives you the chance of figuring out if you like that course or not. Right? And about the projects, start finding project partners as soon as possible. And of course, you can use Piazza or the Google Sheets that are also linked to Canvas. And that's pretty much all for today. So thanks a lot. I look forward. I'm excited to have that many people, and hopefully it's going to be a fun term. Thanks.